Next we want to study the group of units mod p, where p is a prime, look at what type of group it is. And in this section we're going to show that it's a cyclic group. Okay, so that's our primary interest, to show that GP is always a cyclic group. And then we'll also determine how many generators there are for this group. I'm going to use the notation FP for the set of integers mod p to emphasize that it's a finite field that we're working in. And let's first just review a few concepts from ring theory and group theory that we'll need. Okay, the factor theorem is something that you know quite well. So if f is a polynomial over the finite field fp, then a is a zero of the polynomial if and only if x minus a is a factor. And you can pause and go through the proof if you want to freshen up on that. So let's apply the factor theorem to factoring the polynomial x to the p minus 1 over the finite field fp. And I claim the following: for any prime p, this polynomial factors like this: x to the p minus 1 is x minus 1 times x minus 2 times x minus 3 all the way up to x minus p minus 1. So it splits into a product of distinct linear factors over the finite field. And there's an interesting thing to note here. If you match the constant terms on both sides, so you have negative 1 here, and the constant term on the right would be obtained from negative 1 times negative 2 to all the way down the road. So you would have negative 1 is congruent to negative 1 times negative 2 times negative p minus 1 mod p. And we have an even number of negative signs on the right hand side. So this is just saying negative 1 is congruent to p minus 1 factorial, which is Wilson's theorem. Okay, to prove this, it's very quick. We just use Fermat's little theorem. So by FLT, Fermat's little theorem, for any number between 1 and p minus 1, 1, 2, up to p minus 1, we know that a to the p minus 1 is congruent to 1 mod p, which means that this polynomial, let's call it f of x, so f of x is the polynomial x to the p minus 1, that f of a is equal to 0 in over the finite field fp. Because f of a is a to the p minus 1, which is going to be 0 in the finite field. So by the factor theorem, x minus a divides f of x. And since for distinct a we are getting distinct factors in this unique factorization domain, so fp bracket x is a unique factorization domain, thus f of x has the factor x minus 1. It's going to also have a factor x minus 2 all the way up to x minus p minus 1. And then a priori there could be an additional g of x sitting here, right? We just know that these are factors and there could be some additional polynomial. But then you just examine the degrees. The left-hand side is of degree p minus 1 to begin with, and the right-hand side has p minus 1 factors right here. So g of x has to be a constant, and then equating the leading coefficients, which is 1, we get that in fact g of x has to equal 1. I'll just cross it off like that, and that completes the proof. A lemma. Let P be a prime, so P is an odd prime, I should say, and D be a positive integer, dividing P minus 1, then the polynomial x to the D minus 1 has D distinct zeros in the finite field Fp. So in other words, there are D distinct dth roots of 1. And this will follow immediately from the previous result. So since D divides P minus 1, we know that x to the D minus 1 is a divisor of this polynomial. That's an elementary fact. But we know how to factor the polynomial on the right-hand side. It's a divisor of x minus 1 times x minus 2 times x minus P minus 1. And these are all distinct factors here. And since x to the D minus 1 is a divisor of this, it must be comprised of D of these distinct linear factors. X to the D minus 1 is a product of D distinct linear factors. Remember, we're in a unique factorization domain, and these are distinct irreducible polynomials. So the factors are just obtained by taking products of those distinct irreducibles. So it's a product of D distinct linear factors, which means that it has D distinct zeros. Each factor corresponds to a 0. Okay. Next lemma is a result in group theory. If A is an element of finite order in a group G, then we have a nifty little formula for the order of A to any power. So it says to get the order of A to the J, you take the order of the element A and you divide by the greatest common factor of n and j. So if j was relatively prime to n, the order would still be n. And the second part to the lemma is if A and B are elements of an abelian group G of orders that are relatively prime, then the order of the product is the product of the orders. Okay, well, let's go through this one. It's very brief. So if I want to examine the order of A to the J power, the question is, when does A to the J raised to some power m equal the identity element? So let's let 1 be the identity in the group. So when would A to the J raised to the mth power equal 1? Well, that's equivalent to saying that A to the Jm equals 1. And that's equivalent to saying that the order of A is a divisor of this exponent. So the order is the smallest exponent that gives us 1, and every other power is a multiple of that minimal power. And I gave a name. The order of A is denoted by n. Okay, so that's equivalent to saying n is a divisor of Jm. And then let's give a name to this GCD. Let's call that D. And I'll just divide both sides by D. So I just divide n by d and I divide j by d, and then we would get n over d is a divisor of j over d times m. Aha! We've done something like this before. This would mean that n over d is a divisor of m, since these two numbers are relatively prime. Okay, so we're trying to find the exponents that yield the identity, and we've said the condition is that n over d must be a divisor of m. Therefore, the minimal such value of m is just n over d. So that's the order of a to the j is n over d, which is what we wanted to prove. Part 2. A and b are elements of order m and n. Okay, what does this relatively prime do for us? Let's first of all look at the overlap of these two groups. So consider this group. Let's give it a name. Let's let H be the group generated by A intersect the group generated by B. And I claim the only element in this overlap is the identity element. Now, why is that? Well, then H is a subgroup of both of these groups, and so by Lagrange's theorem, the cardinality of H is a divisor of the cardinality of A. Okay, now what was that given to be? A is an element of order m, and the cardinality of H, being a subgroup of the B group, must divide n. So it's a common divisor of m and n. So since the only common divisor of m and n is 1, the cardinality of H must in fact equal 1. So the only overlap is just the identity. Okay, I'm going to need that now. So now our task is to show what's the order of the product A times B. So first of all, it's trivial to note that AB raised to the mn power is A to the mn times B to the mn. Now one of these is of order m. I think that was the A. And B was order n. And so this is just 1 times 1. Okay, so this power gives us 1, and now we want to prove it's the smallest power. So suppose AB to some other power gives you 1. Well, then A to the k is B to the minus k, but this is an element of A intersect B. It's a power of A and it's a power of B, which means that A to the k is 1 and B to the k is 1 by the first observation we made. Since A and B have relatively prime orders, this intersection is a trivial intersection. Okay, but that tells me that k is a multiple of the order of A, so m is a divisor of k. And this tells me that n is a divisor of k. And since m and n are relatively prime, this means that m times n is a divisor of k. QED. Therefore, mn is in fact the smallest exponent that works. So the order of AB is m times n. Okay, now return to number theory. And let's show that GP is a cyclic group for any prime P. So what's the strategy here? Well, what is the order of this group? So the order of this group is p minus 1. Okay, and let's go ahead and factor this into a product of prime powers, say p1 to the e1, p2 to the e2, pk to the ek. So my strategy is to find elements of prime power order. So I'm not going to try to find an element of order p minus 1 all at once. Let's first find an element a sub I in GP with the order of AI being pi to the ei. Now what would that do for us? Well, then by the lemma we just proved, we would have that the order of A1 times A2 times AK is what? Well, we proved a lemma that said the order of the product is the product of the orders provided the orders are relatively prime. And by induction, it would say provided the orders are pairwise relatively prime. So this would just be the product, as I goes from 1 to k, of the orders of the individual elements. Aha! That is just the product of pi to the ei, but that's exactly p minus 1. Thus, the order of this product is the whole group order, p minus 1, so that implies GP is generated by this object. And it's a cyclic group. So, the whole proof boils down to this observation here. Can we find an element whose order is pi to the ei for any prime power? Okay, so let I be any value from 1 to k. And let's consider the polynomial x raised to the pi to the ei minus 1. Okay, now view this polynomial over the finite field Fp. And we have a lemma that says this polynomial has pi to the ei distinct roots. Distinct zeros in Fp. And each one of those zeros would satisfy, I call it a to the pi to the ei should equal 1. So all I need is to find one of those zeros whose order is pi to the ei. Well, let's consider one smaller power. If you look at x to the pi to the ei minus 1 minus 1, this polynomial has pi to the ei minus 1 distinct zeros, which is a much smaller number than pi to the ei. Thus, let's call this polynomial f of x, say, and this one g of x. Thus, f of x has many zeros, this many, which happens to be the Euler phi function, zeros that are not zeros of g of x. Okay, let a be any one of these zeros. Let's call it a sub I. Then what can you tell me its order is? Well, then a raised to the pi to the ei is equal to 1, but if I raise it to one lower power, it's not equal to 1. Therefore, the order is in fact pi to the ei. Thus the order of a, that's a sub I here, is pi to the ei, which is exactly what I wanted to establish. QED. So for each prime power we have constructed, in fact, the Euler phi function, many zeros that would serve as generators for the cyclic group. Well, generators for that part of the cyclic group. In fact, the same proof that we just went through would show that any finite multiplicative subgroup of a field is a cyclic group. So living inside of a field, we would have the same polynomial statement about the number of zeros of the polynomial. And then you could just push the proof through identically. Okay, let's introduce some terminology. So if GM is a cyclic group and A bar is a generator for GM, then the integer a is called a primitive root mod m. And a theorem, how many generators then does a group have when it's cyclic? So if GM is cyclic, then I claim there are phi of m generators for this cyclic group. And this follows immediately from a more general lemma. So if you have any cyclic group of order n, then for any divisor d of n, there are phi of d elements in the group of order d. So in particular, if we want to count the number of generators for the group, you want elements of order n, there would be phi of n generators for the group. And this is immediately implies the theorem because GM is a group of order phi of m. So if I want to ask how many generators there are, it's the Euler phi function of the group order, which is why we get this composition right here. Okay, proof of the lemma. So let G be a cyclic group of order n, and let D be a divisor of n. And I want to see how many elements there are of order D. So I'm going to let G be generated, say, by A. So you'll have the identity, A squared, up to A to the n minus 1. And let's let J be some power right here. And I want to look at what is the order of A to the J power. Well, we proved a theorem that said the order of A to the J is the order of A, which is n, divided by the GCD of these two. So, if I want the order of A to the J to equal D, so I'm trying to count how many times will the order of A to the J be D, is equivalent to saying that D is n divided by Jn. and we're trying to identify the values of j that make this work. So that would mean that the GCD of j and n should equal n over d. So in particular, this is saying that n over d should be a divisor of j. So let's let j be n over d times k, where k is going to run from 1 to d, right, because j has to be less than n, so it'll be strictly less than d. Then this condition right here, star, would be equivalent to saying that n over d k n equals n over d, and then dividing everything through by n over d, that's equivalent to saying that k d equals 1. So k should be relatively prime to d, and k marches from 1 up to d, so that implies there exist phi of d choices for k. QED. So there are precisely phi of d values of j that give us the order to be what we want. Now this is just some closing remarks about primitive roots. So we've seen that the group of units mod p is always a cyclic group, and any generator for this group is called a primitive root. So these generators, we're just talking about integers. And there's a lot of these generators. In the case of GP, you have a group of order p minus 1, so you have the Euler phi function of p minus 1 generators. So the question is, what's the smallest generator that you're going to get for one of these groups? And it's a famous open problem in number theory. So what is known is that there will always exist a primitive root less than p to the 1/4 power plus epsilon. So this double less than just means there's an implied constant right here. And numerical evidence would suggest a much smaller value, that you should have a primitive root existing on the order of the cube of the logarithm of p. But we are a long way from proving a result of this type. Artin's conjecture is of a different type. It says if I fix a positive integer a, like 2 or 3, and as long as it's not a perfect square, then it will be a primitive root for infinitely many primes p. So the positive integer 2, for instance, is going to serve as a primitive root mod p for infinitely many primes. The conjecture is still open, but it is known to be a consequence of the grand Riemann hypothesis on the zeros of L functions having real part 1/2.